6, 5, 4, 3, 2, 1, launch.
Rocket away.
Hello everyone. Today we're going to discuss the fate of the Nova Somnium rocket built by Iowa State University's Cyclone Rocketry Club, the very same rocket you just saw disappear shortly into launch. This rocket, designed, manufactured, and assembled by the 50-student team, tragically met its end at the 2019 Spaceport America Cup competition in New Mexico. The competition sees upwards of 100 international university teams each year seeking to launch their vehicles to heights of 10,000 or 30,000 feet, with the goal of bringing the vehicles as close to these target altitudes as possible. This goal poses a significant challenge to all teams, and in 2019, less than a fifth of all teams successfully predicted their apogee altitude within 10% of their actual apogee altitude. Cyclone Rocketry sought to do this with an Aerobraking Control System, which suffered an anomaly that led to a sudden trajectory change and ultimately the destruction of the rocket. In this presentation, we'll take a look at what went wrong and specifically how integrating runtime verification could have solved this issue. First, let's take another look at that launch. The problem is more visible in this view. As you can see, the rocket lifts off correctly, but roughly 4 seconds into the flight takes a sudden turn horizontally. Houston, we definitely have a problem. Here on the left, you can see the Aerobraking Control System undergoing a final test on the ground before launch. During the rocket's ascent, the ACS experienced an anomaly and actuated earlier than should have been allowed during the rocket's ascent. We will discuss the nature of the anomaly shortly, but long story short, this caused several subsequent errors and the rocket did not achieve its goal, ultimately experiencing
a rapid, unscheduled disassembly. More specifically, the premature actuation of the ACS before motor burnout led to mechanical failure of the ACS as a result of much higher than tolerable forces acting on the brake pads. The brake pads became off track from each other as pointed out in the photo, and the resulting asymmetrical deployment is what caused the rocket to suddenly change trajectory. The high apogee speed led to a recovery system failure, causing an uncontrolled descent and impact. Ultimately, the rocket fell back to the Earth and impacted a couple miles away from where everybody at the competition was gathered. No one was hurt or in real danger, but there was no control over which way the rocket veered, so the rocket could have just as easily veered toward base camp instead of away. While our team was saddened seeing the rocket's final voyage, we were even more intrigued by what caused the malfunction in the first place. The ACS, shown in the leftmost image, was operated by an Arduino microcontroller. This microcontroller runs the logic for when the air brakes actuate. The system is based on the 4 states of flight relevant to the air brakes: the launch pad state, the accelerating or boost state, the coast state, and the descending state. Each of these are shown visually in the diagram on the right side of the slide. When the rocket has determined that it's in the coast state, it uses the onboard accelerometer and barometer to calculate the apogee, the highest point of the rocket's ascent. This logic then compares the calculated actual apogee with the estimated apogee, and determines when the ACS will actuate. This is how they should have worked in theory, but as we know, garbage in, garbage out. When the rocket was launched, the sudden large acceleration caused by the impulse of the rocket's motor caused the ACS's power to flicker, which unexpectedly reset the system while the rocket was in motion. When the system turned back on moments later, the rocket's sensors, which require a brief calibration period prior to use, reoriented themselves improperly. This is essentially like trying to zero out your accelerometer, but the accelerometer is going through a massive acceleration instead of remaining stationary. This system reset meant that the input data for the state and trajectory calculation was incorrect for the rest of the launch, and led to wildly incorrect acceleration data and premature actuation of the air brakes.
If the software on board the rocket's ACS had the ability to monitor the values, for example, velocity, pressure, and altitude, it was measuring, and check for validity in real time, then conceptually, the ACS could have caught an invalid state before ACS actuation, taken a mitigation action, and prevented the destruction that the rocket experienced. For this work, we considered the mitigation action to be simply disabling the system, because without the ACS, the rocket would simply overshoot its target altitude and recover safely. Throughout this presentation, we will detail our efforts to do this using runtime verification. We also recognize that there are other solutions which could have fixed this problem, such as preventing the power from flickering in the first place. But the main benefit of our approach is that it adds a layer of safety between unexpected real-world errors and resulting incorrect control inputs. To perform our analysis, we use the Realizable, Responsive, Unobtrusive Unit, or R2U2. R2U2 is an extensible framework for the runtime system health management of cyber-physical systems and was developed to monitor expressive properties of systems in real time, with little overhead and significant constraints. R2U2 can run in hardware like FPGAs or in software, such as the C++ Arduino framework used in our ACS. R2U2 can monitor hardware, software, or a combination of the two, and it can analyze a wide range of system requirements during runtime. Originally deployed on unmanned aerial systems, R2U2 is designed to run on a wide range of embedded platforms. The spare processing power and memory aboard Nova Somnium and sounding rocket payloads in general is extremely limited, so overhead is one of the biggest considerations that we have to make when picking a tool. Additionally, Nova Somnium reached a top speed of roughly Mach 1.5, so the ACS needs to make decisions quickly in real time. For that reason, R2U2 was the only viable tool for working to integrate runtime verification into this rocket.
The R2U2 tool reasons over specifications written in mission time linear temporal logic, MLTL for short. Temporal logic is used to formally describe requirements for a system, and our rocket is no different. We must craft specifications that are robust to insignificant faults, like sensor data noise, to prevent false positive alerts from the RV engine. This concern naturally arises owing to the relatively cheap cost and fallibility of the sensors. We can handle this in part by tweaking Boolean atomic definitions. However, MLTL offers powerful temporal filtering that makes such small fault tolerance easy to alter. We use this to adjust the acceptable time frame we expect something to happen within. In a couple slides, we'll look at these features through an example. Nova Somnium's ACS includes an Arduino-based central processing unit and two sensors, an inertial measurement unit, and a barometer. This provides the rocketry team with data on the acceleration and velocity vectors of the rocket, altitude, pressure, and temperature. As stated earlier, these sensors recognize four possible states of the rocket's mission: launchpad, boost, coast, and descent. This information is then fed into the flight computer operating the ACS, which additionally keeps track of the time since launch, the calculated vertical velocity and global coordinates, and the actuation status of the ACS. We use these system variables to describe system operation in our formal specifications written in MLTL, which are available on the project website. These specifications are derived from rocket-level and system-level requirements, written first in English. Note that we have full signal coverage here, meaning that each of our variables is used in at least one specification. All of our specifications could be classified into three separate categories, which are formally outlined in the work shown at the bottom left. An operating range specification indicates that a sensor has an expected operating range, and it should fall below or exceed a given threshold. This may indicate a hazardous system state. A rate of change specification indicates that a sensor's rate of change may also be bounded. Additionally, one could monitor to make sure there is change between two consecutive sensor measurements, or that the amount of variance between sensor measurements is not skewed in one direction or another. A control sequence specification indicates that the system is following its overall intended operating procedure over time. For example, the rocket launch phases should all happen in the correct order: launchpad, boost, coast, and descent. These types of requirements are particularly well suited to temporal logic. We practice specification validation through the development phase, as specification creation is a circular process. We first validate the correctness of the Boolean atomics by generating atomic traces corresponding to ACS runs, checking manually that each atomic accurately represents the ACS data. We then stream the atomic traces into R2U2 and plot the specification verdict at each time step to analytically determine if the specification has correctly captured the requirement. As we test specifications, we can trace errors back to the MLTL formulation, Boolean atomic definitions, or English requirement.
Here is a summary of the results of our MLTL runtime specifications for Nova Somnium's ACS. An in-depth list of specifications with the original English requirement and the atomic definitions alongside of the MLTL specification can be found on the project website. As you can see from this graphic, we generated 19 specifications in total, 6 of which are violated by the Nova Somnium dataset. We'll take a look at two of our specifications more in depth, which we consider to be telling of the failure that is present in the data. The first is Specification CS7. This specification states that once the rocket enters the boost state, it shall remain in this boost state until the motor is 90% burnt out. Its MLTL equivalent is directly below. This is a control sequence specification based on prior knowledge of approximately how long the solid rocket motor should burn for. With a known time step duration, in this case about 50 milliseconds on average, we determined from the motor specifications that 90% of burn time would coincide with about 5.7 seconds into flight, equivalent to about 114 time steps. This information is encoded into the atomic proposition 90% of burn time and acts as a minimum condition to be met before any state transition occurs. The bound on the until operator represents the time frame that in-boost state must change within, allowing us to specify a maximum amount of time that the rocket can spend in the boost state before R2U2 determines this specification is violated. And so, in this way, we say that the rocket should be in the boost state for at least 5.7 seconds and at most 6.5 seconds, providing a range of time for the system to make a state transition. These values can be easily adjusted to enable a wider or tighter window to account for different amounts of uncertainty, or to specify a different choice of rocket motor. Here, we compare the rocket state data with the runtime verdicts produced by Specification CS7. Again, remember that this rocket's ACS reset, so the data doesn't necessarily coincide with what the actual rocket did, but rather with what it thinks it did at each time step. As you can see in the upper graph, according to the ACS data log, the rocket did not remain in the boost state for at least 5.7 seconds, in fact lasting under a second. Running our specification with R2U2, the boost state transitions to the coast state much faster than should ever happen, and actually happened, according to our video, so the false verdict is given, shown in the lower graph. Note that if the rocket experienced a motor performance anomaly instead of the ACS power flickering, this false verdict would still be useful, as if any use of the ACS would be unhelpful in that situation. The most important result we have found and are showing here is that had R2U2 been embedded and running on the rocket in real time, the RV false verdict outputted by R2U2 would be found before the error occurred and therefore could have been used to disable the ACS prior to actuation. This would have saved the rocket and prevented a dangerous uncontrolled trajectory change.
Our second highlighted specification states that the vertical velocity shall be non-negative during the launchpad, boost, and coast states. This specification is essentially sourced from common sense, as a stationary rocket, and one that is ascending, shouldn't return a negative vertical velocity value, as this would go against physics. The MLTL version of this specification is shown below the English. You may notice that we have no temporal operator in this specification, which the stream-based nature of R2U2 interprets as globally over the entire mission. Here we compare the vertical velocity data with the runtime verdicts produced by Specification OR-4. Looking at the upper graph of vertical velocity and comparing it to what we saw in the video, we can see that this measurement is wildly incorrect. We see multiple violations of the specification, as evidenced by R2U2's output in the lower graph. An indication of a negative velocity during any of these rocket states would indicate the vertical velocity is not being measured correctly, meaning that the values indicating when to actuate the ACS are based on incorrect data. If R2U2 were running on the rocket in real time, then the RV verdict outputted by R2U2 could have been used to prevent ACS actuation, preventing their improper use and saving the rocket from the damage it encountered. With our manuscript, we've contributed formal rocket specifications for the first time and applied RV to a domain that is as of yet untouched, using the real data set from the Nova Somnium rocket. In particular, we have shown that runtime verification can detect and mitigate real-world software errors before they become catastrophic. In future work, the R2U2 tool can be embedded into a new competition rocket's ACS with our specifications to provide real-time reasoning of the system and monitor for critical faults. We will author additional specifications to more precisely identify errors and allow for advanced mitigation protocols. We also look to map R2U2 outputs to a wider range of mitigation strategies. It is our hope that a future ISU competition rocket will have R2U2 embedded into the avionics to monitor for these precise errors.